Hello, and we're back with the Sorado. This is do all the things. Though it seems like I might do a lot of the same things. We have determined that the transformer is acting up on this guy. So now we have to move forward, diagnosing and possibly replacing it. So in a previous episode, I went ahead and I replaced and rebuilt the power supply on this guy. It was in dire need of a recap, and they don't really make the kind of capacitors that this power supply was designed for anymore, so it needed a complete redesign. So moving forward, we hooked up the original output transformer, which is said to be blown, and indeed it kind of farted out on us. Now, before I get into completely gutting that guy out, there is another experiment I kind of care to do, and that is, well, the sounds that it was making reminds me of bad screen grid power supplies I've tried to design in the past while trying to figure out how to bring my screen grid voltage down without using a lot of dropping resistors. Kind of reminiscent to what, Ampeg and Trace Elliott and guys who make big bass power heads would do. Now, well, diagnosing this thing in the past with another transformer, I didn't have it all set up properly. All I did was I connected the screen grids to the plates to make, basically triode mode, which is going to be half power, low power, but it made it really easy to hook up a replacement transformer really quick in a scenario in which I didn't have a screen grid power supply. This amp has no screen grid power supply. It is completely dependent on the 40% taps coming off the transformer in order to run those screens. Now, we don't see this very often in guitar and instrument amps. It's more of a hi-fi kind of thing. And according to what I know, it's a way to get the power amp to run cleaner, less distortion. This is a bass amp. I guess they wanted it to run as loudly and as cleanly as possible. And I suppose the engineering to do that exists. But this method here is often used in hi-fi application where they value fidelity over power output. Now, two KT88s running at 600 volts. It's entirely possible we'd be getting a full 80 watts out of this amp. The average KT88's rated for 42 watts. So I guess this would be an 80 watt amp. If you could get 80 watts clean power out of it, I guess you're doing well. But I've never heard this amp actually running properly. It's been broken the entire time I've had it in my possession. Hopefully we can remedy that today. But I'm gonna start off by getting some 1K resistors here. And I'm gonna bypass those screen grids. I'm gonna bring them right to the plates, and then we'll see how the amp works then. Now the Sorado has this strange connection in the feedback circuit I've never really dealt with before. They basically not only pull feedback from the 16 ohm tap here, they also pulled feedback from one of those screen grids. A 390 microfarad. That's an interesting way to write picofarads. That's this guy right here, and well, with what we're doing, it's kind of redundant. Especially if I proceed with this amp the way I think I'm going to, this kind of becomes useless. You never know. Maybe the power transformer is half okay, and it's just those screen taps are done. Alright, so this is going to be a triode mode amplifier now. So we got sound. No. Hear that? Volume cranked. I'm getting no volume. Okay, well, let's proceed. Alright, well, let's just gut this transformer off of this. Ploop, 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 ploop. Alright, it's completely disconnected. I am going to see if I can just kind of splice this guy in here. If I can find a way to position it that it's not going to touch anything. It's totally touching everything. I don't think that's going to happen. Yellow is 16. We put that on the feedback right over here. Green is 8. All right. This is very just kind of ploop, ploop. Yeah, that looks great. That looks great like that. Just it's not touching anything though. So let's try not to blow this thing up. That's at 8. Turn it to 10. difference. I don't know that it sounds good, but it's working. And of course, because we're in triode mode, that's not even close to its full volume. We got a couple deficits working against us before we reach full volume. So, hey, let's work on getting this thing mounted now. Clearly, that old transformer has got to go. Okay, so we got some bolts here. What else? Chances are, of the construction era, it is not metric. Ooh, I'm cracking the factory Loctite here. Except these puppers are just spinning out on me now. Oh, and I'm not going to be able to get at those guys down there. Well, we got to take a different approach here. Gonna have to do some combination of getting in there with a strange, where is the strange? A little bit of a strange here. A little bit of a... Hey! Aha! Progress! Wish I had a more effective way to prop this thing up. This is not gonna end well. Come on. Oh, frick! Ugh. Get out of there! Just spraying bolts everywhere, bud. Oh, this thing's a unit, man. That's like easily what would be regarded in some circles as a 100-watt transformer compared to the replacement. And trainers were no slouch. They did not put weakling transformers in their amps. Will this be able to hold up, or will it just will it blow? If we could blow, like, what would blow a unit like this? Other than, as discussed in the previous video, just a ridiculously poor design failing over time. Model WTC 1276, November 1970. Well, hopefully it gave someone a decent service life. The chassis is magically much lighter now. Crap falling everywhere. So, footprint, slightly different. They have another set of bolt holes here. I guess they spec'd out this chassis for a couple different designs. It's clearly not fitting in the stock holes. Ooh, it almost fits in those other holes. Like, it almost looks like... Yeah, we can use at least 2 of these holes, but not necessarily the other 2. Oh, it's too bad. It almost wants to fit in the old holes. It almost seems like if I bend these tabs out a little bit, maybe it will. Nah, we gotta make new holes, bud. Don't you just hate it when mounting holes are just so close but so far away? Alright, well, here goes nothing. Put one there. We'll put one there. Consultant, where's your punch, buddy? Hey, nice. Let's make sure there's nothing directly under where I want to drill. Close, but we're good. Acquire the bit of appropriate size. 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 Alright, this chassis is surprisingly easy to drill. Okay, I think we're doing good with only 2 new holes. Alright, installing transformers is always a fun time because they're the heaviest object on something that, you know, doesn't really have support. Ploop, ploop. We'll get some nuts fastened underneath. Hopefully, if I hang it partially off the bench like this, I can get those nuts on without it completely screwing off on me. Need a little incentivization here. Okay, does one. I gotta find some of those nuts. I kind of sprayed them everywhere, didn't I? I found a part of one of the nuts. Yeah, the workbench is starting to get a bit hectic there, but stuff is finding new homes for itself. Oh, there's one hiding in the chassis down here. Also, some of those odd angles right here. It's hiding underneath the input jack, sir. I think we can work with it now flipped over. So I gotta figure out, what do we do with this wire retainer again? I can't remember. It was like that, and it was holding down the primaries, I think. Yeah, seems legit. Gotta bolt it all together. Gotta put it on its side. Oh wait, this side's no good because I can't get the screwdriver in there. It's a gotta wrestle this thing. Oh boy, this is not fun. Okay, back to this kind of way of doing things. It's got the screwdriver in there, and then we gotta hold on to this guy. Can't get a proper wrench in there. I don't even know if I trust if that's actually tight. I'm just rounding off these freaking... Problem is, this trainer transformer has too small of a footprint, and the bolts are hiding underneath this ridge, so it's hard to get a screwdriver directly in. Actually, I think last time I installed a transformer like this, I put the nuts on the outside. Maybe I should have done that. Then at least I could wrench on them. It's pretty much in place now, so we'll call it good. Yeah, it'll be fine. They're tight enough. A little bit of Loctite, and they'll never come loose. So, if I remember correctly, this has to come down here. I'm actually going to double this back around. transformer main connection is over on this lug, which I kind of want to come under. Conveniently, this has all the correct secondaries. We're going to be slacking on them a bit because I don't want to commit this transformer completely to this build. The fact of the matter is, one day, what I might want to do is get a proper transformer for this, one that's rated for it. And if we look at Hammond's line of easy wire secondaries, 1600 series, we got this guy here, 4300 at 60 watts. Though it's a 2-tube amp, you might consider it 60 watts, but pretty sure that transformer at 300 milliamps DC per side is going to handle a lot more than 600. Otherwise, the RA here, 100 watts with a 5000 count, 318 also milliamps per side. That might be what we're looking for right there. Beastly. And they have the screen taps, so they're a drop-in replacement. So we have 4 ohm and 8 ohm outputs on this amp, with a scheme that makes sense to me. So if you plug in to here, you get 8 ohms, but if you plug it to here, it snaps over to 4 ohms. Oh, I see what they're doing here. If you plug it to both, then it stays in 4 ohms to plug into 8 ohm cabs. All right, that makes sense. And then, you know, it has a 16 ohm tap, but it's only used for feedback, which I guess makes sense. There's not much application for a 16 ohm tap in bass. Your cabs are usually pretty higher impedance. I, in fact, have a pair of 4 ohm cabs. That would be a 2 ohm load. I need even lower impedance than this. All right, now we just have to figure out what to do with the primaries. So if I recall correctly, blue was on this side, and that phasing worked just fine. Problem is, brown isn't going to reach all the way over there. We need to extend on it some way, somehow. There's some terminal strips over here. I think I'm going to use one of those. We'll attach the wire there and run another over to the tube socket. Oh, bust out some of our nice black wire here. 20 gauge. This is actually a very convenient spot for this lug to be. All right, so this black wire will come over here and chop it right about here. All right, this new transformer is hooked up. The amp should work identically to the way it did during the last test. So I'm not gonna bother testing it again. We need to move forward. Now there's a circumstance that exists in amp design, especially when it comes to these big power tubes and these kinds of amps when you're running a high plate voltage. You know, you have certain Ampegs and Trace Elliott bass heads, and they have this way of pulling 50 watts out of what would otherwise be a 35, 40 watt tube, 6550s, KT88s, etc. And you know, I can't claim to understand exactly how they do that. I'm not a complete expert on these amps. There's a lot of designs up there that's just kind of like, whoa, what's going on there? Kind of like this Trace Elliott V4 over here. The Ampeg SVT has a similar setup, but this one's a little bit simpler, so it makes it easier to illustrate to you. So here we have 4 6550s, and this is known to be a 200 watt amp. Here we have one power supply. That's pretty much just for the B+. It says 485 volts AC before rectification. This guy's gonna run about 650, 700 watts after that rectification's done. And that's just for our plates. However, if you look, there is a separate screen grid power supply, a whole separate secondary winding on the power transformer, whole secondary bridge, cap arrangement, RC filters, etc., just for the screen grids. And they're running them down to about 350 volts. Now, this makes sense because if we look at the specifications of a 6550, it has a max 600 volts, and I'm sure they push it harder than that, but the screen grid's max 400 volts. Now, generally, it seems in practice you can get away with exceeding 400 volts in certain other amps that aren't quite as high plate current. You can run your screen grid at what I'll call unity, which is basically just a small voltage drop through the 1K resistors. You know, people run 6550s in their Marshalls all the time. I know I have. It works great, but they're definitely going to be exceeding 400 volts on the screen grid. But in these amps, when you are starting to push that tube to the absolute full-on capacity it's capable of, even exceeding its wattage dissipation, you have to keep those screen grids under control. And that's kind of the design of this amp. That's what it's doing with those screen taps on the secondary of the output transformer. They have 40% the voltage, and it is going to be around 350 volts. Actually, I think it's time to do some maths. So 600 times 0.4, 240 volts actually. That's down there. I don't feel the need to go quite that low. My target is about 400 volts. So how are we gonna do this? That's a dragon I've been tracing for a while, but I finally figured it out. We're gonna use voltage regulation. An Infineon 70R750 P7S 700 volt cool MOS P7 power transistor with a capacity of, what do we got here, 15 amps? Oh, that's pulse amperage. Come on now. Give us the real amperage. Maximum rating. Continuous current. 3.5 amps. Well, that's well enough. And operating temperature of 150 C, which we shouldn't exceed, but it's going to require some sort of heat sinking, which is why it's important that it has, you know, a plastic kind of mounting point here. Other more standard and lower voltage MOSFETs will have a metal mounting point, which we can't use for this because it's usually directly connected to the center pin, the drain. And since we're going to be having positive potential on that, if we touch something like that to the chassis, we're going to have a bad day. So if you're going to do something like this, you need an isolated MOSFET. Now, full disclosure, I haven't tested this particular MOSFET. I've tested this theory before. Here's my prototype arrangement using some random 500 volt MOSFET I found on a power supply board, and it just worked. Or at least it seemed to. So I've been trying to figure out how to build a screen grid power supply for a while using, you know, the transformers available to me to do retrofits to amps, especially, you know, you can get from Hammond high voltage transformers that I could use to build an amp to push some of these tubes to their maximum output, but they don't have the separate screen grid winding on the transformer. And like I thought about using a MOSFET and it's kind of like, why not? In the past, I've built successfully screen grid power supplies using vacuum tube regulation, using a spare EL34 tube, adding another socket, using that as a regulator. Now the voltage on it's going to swing a bit more based on current load, and it loads down your heaters even further, especially in EL34. They have like 1.5 amp heaters on them sometimes. But then one day I'm surfing through the Facebook and I found some group that was discussing or showing off audiophile amps, the fancy stuff. And I came across this schematic. Some guy named Doug D. Young. This is a power supply for one of those fancy audiophile power amps. Try to get some nice, pure, unrippled current to those audiophile power tubes. Now, that's a bit overkill for our applications, but when I saw this, I'm looking at it, I'm like, oh, it's that simple. Well, why the heck not? Let's just chuck a MOSFET in here, bud. So I prototyped it on here, and I tested it on the screen grid of just an EL84, and sure enough, it worked. Current passed at the voltage I told it to be. And it's such a simple circuit. Here's the regulator to scale. We got our 3 pins. This one's the gate. This one's the drain. This one's the source. This is an N-channel MOSFET, which means usually we have, you know, we connect this guy to negative and we switch the negative, yada, yada, yada. What you need to know is that the drain is the anode and the source is roughly the cathode. So we have some voltage input. It's going to be our 600 volts and it's going to connect directly to the drain, and then the source is our voltage output, whatever we end up coming up with. So to regulate the voltage of this, to tell it what to do, we need to build, you know, a simple voltage divider circuit, and then that's going to tie to our negative or our ground. Now we will have a capacitor to stabilize the voltage we create there, and then, you know, just a buffer resistor, and that feeds into the gate. The buffer resistor, 1K. This I'm going to be using a 10U 500 volt. The hardest part is calculating the value of this voltage divider. Now, we do not want a lot of dissipation. The lower the value of those resistors, the more heat they're going to generate, the more current they're going to pull out of the circuit for no good reason. And the fact is, this MOSFET needs mere microamps to be driven. So I've already calculated this math. Let's shoot for 1 milliamp of current draw, which quite simply, according to the math, if we have 600 volts and we divide that by, you know, 1 milliamp of current draw, we need about 600,000 ohms or 600K. And that's going to be roughly right. So for this high voltage regulator, we want from here to here about 1K per volt. Price is Right rules, or opposing Price is Right rules. We want at least 600K, if not more. We can go higher and it'll work fine. Then we need to figure out what voltage we want. So we start off with 600 volts, and well, I want somewhere between 350 to 400 volts. So basically we use basic percentage math. 400 divided by 600 is going to give us our percentage. This is about 66%. 350 divided by 600 is 58%. So we need 58 to 66% of the voltage. If we have a 600K voltage divider stack and we want, say, 58%, simply times 0.58, and we have 348K. So basically, this would be a 348K, and then this would be whatever the difference is to equal 600, which would be 252. Now those are oddball values. We're not gonna have those kicking around our parts bin, are we? No, we're not. So let's delete those. But you know, 350, what do we have? We have 220 and 470. That's easy enough. 220 plus 470, oh, that's 690. So we're gonna work with a voltage divider stack of 690. Now, if we take that 690 and we find out 58% of that, oh, it's 400. How about the 66%? 690 times 0.66, 455. Now, we have a 220 and a 470. So, using the percentage math again, if we take, say, our 470, divide that by our 690 stack, we get a value of 68%. So if we take our 600 volts, multiply that by 0.68, that's 408 volts. That's pretty close to target. So we could likely just use a 220 and a 470 here and get what we want. Maybe I want it a bit lower. Let's try a 330 and a 470. 330 plus 470K, 800. Cool. So what voltage are we gonna get in between that 330 and that 470? Well, we're gonna go 470 divided by 800 is 58.75%. So if we take our 600 volts, multiply that by 58 point blah, 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 352 volts. That's pretty close to target. That's actually perfect according to that Trace Elliott schematic. That would be right about where we want. And voltage sag would probably bring it down just under 350. So if we use a 330K and a 470, we should get 358 Vs. Now you might want to further expand on this. One thing I was thinking of doing is we have our upper resistor, probably going back to a 220, and then we have a lower resistor, also the 470, but in between, putting a potentiometer. I have 100Ks in stock. That should give me some margin of adjustment. Say if I want 400, say if I want 358. But from right now, it looks like 330 and 470 are gonna win the day. So let's test on this just to be sure. We're gonna basically be jumping off our B plus here, post choke. That would be right here. And our input is, oh, first of all, this is not a 330, this is the 220. Where's the input again? Oh, it's this middle ground right here. Talking about ground, we definitely need to ground out these connections. Let's grab ground. Let's power it up. Here's hope this thing doesn't instantly poof. What do we got here on the old meter do? So our input, sure enough, should be like, yeah, 617 volts. We're running a bit hot with no sag. So what's our center point here? Oh, look at that, 349 volts. So what does that mean our output is? Oh, look at that, 350 volts. Maybe the math worked, bud. Now, is this gonna be enough to chooch our screen grids? Oh, probably. Let's find out. So these screen grid resistors, we're going to disconnect them. We're gonna go ahead and use unused pin 6 to connect these guys. I don't know if these 1K resistors are big enough for this particular application. We have a piece of feedback circuit here that needs to get abandoned. Sorry. Gonna have to figure out what to do with that wire. It's connected here. Ah, f***ing Ugh, there's still some voltage in here, but you know, based on my experience, these smaller screen grid resistors are going to be actually perfect for this application on the grounds that that controlled screen grid supply is going to dissipate so little current in practice, they're not going to really work very hard. It's when you get those amps that run unity and then you crank them up, that's when you start really stressing out the screen grid resistors. These are what, 2 watts? All right, we got our screen grids in place. Now let's proof of concept our voltage regulator. This black wire will now be the output. We'll clip it onto one of the tubes here, and then we will jumper these guys together. So we got screen grid supply on both tube. And we need to grab our ground supply, and then we need to grab our B+. Now we need to put some tubes in it. Oh, the amp's shorter now. Can't fit tubes under there. All right, tubes are in. Let's fire it up. Now we're gonna have to recheck our bias because we're definitely it's gonna go colder, and we might have the side effect of not having enough, having too much negative voltage, but I doubt it. Let's check on our maxivolts here first. Input voltage, 608. Output voltage to screen grids, 353. Bias dissipations. Oh, look at that. Okay, so having a very controlled screen grid completely nerfed our bias supply. We need less negative voltage now. That's basically this 15K resistor there. Arbitrarily grab another 15K resistor, and we will cut that bias supply. Looks like we're gonna have to make some tweaks in the bias supply too, buds. Bring down the value. Okay, there we go. Bring up to 40 milliamps. Okay, we got bias supply now. It's on 7 right now. It's already way louder than it was before. Let's probe our voltages here, bud. What does our B plus say in practice? 590. Strum it. 560. Now what's our screen grid output? 340. It works! It works quite well, actually. Yes, yes. Finally, I've unlocked the caramel secret. I got a reliable voltage regulator supply for all the screen grid needs. How hot did this MOSFET get? A little bit warm, little bit, but not a lot. Now mind you, we aren't playing very long. So now, we have to officiate it. We're gonna be busting out another one of those little hobby boards, bud. As is the usual MO when using these hobby boards, I got a couple of drilled holes in it. I gotta figure out where we're gonna put it, probably right there. Just right there with the rest of the power supply. That's really no more an ideal place for it. Let's mark those positions, sir. Ladies and gentlemen, once again, the consultant. So far, the cycle of violence is just unending with this amp. All right, let's get some holes in it. Why do I even call those hobby boards? I guess they're for hobbyists who can't print real circuit boards. That's just almost literally making the hole worse. This is some soft steel, man. Not responding well to my usual methods of chamfering. All right, let's get some screws, sir. Again with the theme of 632. It's a tight hole. We're gonna be using little 1/4-inch standoffs because I have a plan and I need the board to sit a bit lower than usual. Oh, I got ourselves a fair amount of slack on this side. Hopefully it fits. All right, yeah. I gotta get out our vise.
The vise is the rulers.
Okay, so we need some capacitors, possibly 3 of these. We need our FIT, we need our resistors à trois, and I want to mount this very subtly on the end there like that. I want a lot of slack on that MOSFET because of the way I plan on mounting it. As you can see, I'm already kind of going upside down and backwards here. I feel like, can I spread those legs out? Should I spread those legs out? It's high voltage after all. Maybe a little bit of clearance will be advantageous. Okay, it's always the fun part, these little puzzles. I think I got a layout figured out. Oh, I gotta bust out all our wire. Okay, I think I got this nipped in the bud. And I know I don't explain very well how I do this because it's pretty much you gotta sit here and solve a puzzle. You got the schematic down, you just gotta connect it all up. This isn't really a how to make one of these. So I went with 2 10s to make a 20 output for the screen grid, and then that 10's the stabilization. And then yeah, you just got your 2 resistors, 3 resistors and 3 capacitors and a voltage regulator. Easy. Had to use a jumper to get the input power over to where this resistor was. And then you know we have our gate all kind of converging right here on this large glob. This guy goes to ground, little ground bus there. Jumper over to ground out the, reservoir cap here. And then, output bus right here. So, red is going to be our input, ground, output, done. Now I just have to install on it. Just going to require a little bit more trickery. Part of the trickery is the act of bending down this regulator so that it smashes right against the chassis. Can we just do that, easy? Pretty easy. Slam that down hard, and then, Now make sure you make enough room for your bolts, right? You don't want them shorting out or touching anything. They're well clear. So the idea is the MOSFET needs heat sinking. You can't run a raw dog. And the easiest way to heat sink it is to bolt it to the chassis. And as long as the chassis does not exceed 150 degrees Celsius, which means you could boil water by merely touching it, then that MOSFET's going to get the heat sinking it needs. But that means we need to drill yet another hole. Right about there. Can we get this hole through without... Oh boy. I was able to very carefully pilot the hole though. So that's going to be exactly center. That's why I got a short 1/4 inch standoffs instead of getting the... Usually I'd put 1/2 inch. But then you know what? It's a good thing I didn't because these caps are tall and it wouldn't have cleared the chassis. I should keep that in mind and order more 1/4 inch standoffs. And we drill yet another hole. Now I need some mounting solution for that. Little tiny nut and bolt. We're going to need heatsink goo. Same stuff we use on computers. I'm pretty sure, yeah, nothing's touching. Put the screw through the hole, fasten the nut down. Oh, now we just tighten up on that little tiny screw. Doot, 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 doot. Not too tight, it's just plastic. There we go. Our voltage regulator module's in place. MOSFET's on the chassis. It is going to sink heat out of it. Now we just have to hook all these wires up and we can let it rip, buds. Oh, yeah. Okay. So our blue wire has to come from Reggie over to, it just has to jump these two together. I do believe I've determined a snippy snip point here. Alrighty. Now where's our snippy snips? Oh, the bench always gets so chaotic. I want to see if I could do one of my mid-strip tricks here. Mid-strip is, we didn't actually cut the wire. Just kind of stripped it midway. I give it a bit of a twist. We can just wrap it around there. That's 1 screen grid, and that's 2 screen grid. Fancy it up, just kind of have a hovering wire, but I'm sure that's going to be just fine. Well, maybe I should made it all pretty and tied it down here with a little bit extra slack. Oh well, hindsight. And now it is like it is perfect because this wire will go right here and this wire will just go right here. Right, bud? Tack them down. That reg is hooked up now. We should be done. We just need to do something about this bias circuit. Now, if we look at the bias circuit, we have straight up a bias tap. There's no dropping resistor on there. So what we see is what we get with the voltages on this thing. Let's check with the meter to see what those voltages say. 83, negative 83 volts is what we got. And then there's a 1K resistor that kind of buffers it. About all we can really do is change the value of this 18K here, which allows you to determine how much you're shunting to ground. It says our bias pot's only 10K. That's not a huge range of adjustment. So the stock resistor's an 18K. If I take an 18K and then on the other one, I put a 15K, 8.1K. Hit the spot we needed. Okay, that's fine. I got some 8.2K resistors in stock. That should be about right. All right, let's pull this guy out. Of course, I didn't do a very good job tacking it down, so it just slips right out. Hit the point at 2K. Get it bent up. So tight down here now. Not a lot of room to move. That should do it though. All right, that's in place now, sir. Now, we should be completed and ready to go. Let's throw the meter down, reinsert the tubes, and let's fire it up and give it the testings. Bring it back up to 40 milliamps. Close enough. All right. What do we have on our B pluses? Ay, you f***ing That was interesting. I slipped with my meter and I created an arc between heater and B plus. That probably fried the fuse. That's why we have fuses, by the way. Oh yeah, bud. She's cooked. B plus is 606. Let's check, make sure we have still have bias over here. 35, 36. Yeah, okay, the tube's fine. B plus, 603. Well, let's get on that tube again without slipping. 597. Screen grids. Oh, they're getting exactly 350 after the 1K resistor. Perfect. Nailed that math. Wonder how hot that MOSFET's gonna get. Now we can get a feeling for how much current the screen grids are pulling by metering across the screen grid 1K. We're seeing a drop of 1.17 volts. 1.17 volts divided by 1,000 is 1.17 milliamps. Derp, it's a 1K. So that's like what? That's nearly 3 milliamps this regulator has to manage. So I think we'll be okay. And once again, the guitar. We're We're at 2 in volume. 50% volume. Let's bring her to 10. Percussive. Let's test on this a bit more. So we'll just go general B plus here. 598. Now let's strum some real loud chords. We'll say an average of 560. Then we'll check the bias on that same tube. I'm gonna say we're averaging 80. Is 44 watts a tube. Huh, this is an 88 watt amp. The thing is, we still have like a 12AX7 hack in here that I don't know is putting enough drive actually to the tubes. So even though they're maxing out, there could be more volume to be had. I wanna check voltage drop across the screen grids really quick at max volume. We're getting average 15, peaks as high as 20, with which a 1K resistor, that's gonna be like 15 to 20 milliamps a tube. That's pulling quite a bit from the screen grids. So we're getting 30 to 40 milliamps being pulled through this little recto here. But it should like not be able, like there's a little bit of warmth there, but it should not overheat. It should be doing this just fine. How about voltage sag? So that is before the resistor, 352 volts. Now we're gonna see some sag because the power supply in general is saggy. It sagged down to 332, but what's the voltage feeding it? From 602 to 562, that's a 40 volt sag. So 350, the screen grid's only seeing a 20 volt sag. Our B plus sags 40 volts, but our regulator only sags 20. This is, that's better than the rest of the power supply. Oh wow, but it means it's doing its job. So I hope you enjoyed this. Stay tuned, because in the next episode, we're replacing the 12AX7 in there that is testing on the amp with a 6U8A, which is a theoretical side grade from the 6AN8. And then that will put this amp back into its proper designed operation. Well, for the most part, let's face it, this amp's never going to be the same again. But in ways, I think it's going to be better. In other ways, well, it's got to be good either way. It's got to be good either way. And when someone, a long time from now, opens this up to inspect it and sees this, well, it's gonna be interesting. They're in for a surprise. Oh boy. Oh boy. Wow, that came together nice. But surely it's gonna go louder than this, right? It's supposed to.